let us start our journey into floating point numbers. Now, if you've ever been taught mathematics at a college or a university, you know what it's like sometimes when you go in and do the course and the lecturer does a lot of theory on the board for half an hour or so and you don't really understand it, and then he does a couple of examples and it all seems quite easy, and whenever you go back to the theory you start to understand it. Well, I think floating point numbers is a bit like that. It's actually much easier to understand it by actually looking at examples. But before we get into the examples, I think we'll go over just some of the theory, so it'll make some of the examples make a little bit more sense. So don't worry about this, it's actually a lot easier than it seems here. So let's get started on it. So let's start off looking at something called fixed point numbers. Now, we're all used to seeing the decimal numbers, say for example 132.625. Now we know that is 1 times 100 plus 3 times 10 plus 2 times the 1, and then there's a decimal point, and then we're going to have 6 times 1 upon 10, 2 times 1 upon 100, and 5 times 1 upon 1000, and I've got those represented here. So we've got the units, the tens, the 100s, 1 upon 10, 1 upon 100 and 1 upon 1000, and each of those are associated with the 132 and the 625, and the point is at this point here, and it's just understood. Now we could do the same thing with binary. We could represent this number 132.625 in binary. Now this is the actual binary representation of that number here, and you can see it's got the decimal point. So in the binary representation, I've redone this table here, but we've got the actual binary values. So the binary values, instead of taking the values of units, tens and 100s, it starts off taking the set of units, but then it goes to 2, 4, 8, 16, 32, 64, 128. And we can use this here to represent the 132, because the 132 is going to be 128 plus the value of 4. So we'll have a 1 here and a 1 there, so it's 101 times 128 plus 1 times 4. Now the part here that's interesting is the fractional part. We can actually represent the fractional part here in binary in the same way as we represent the fractional part in decimal. So we could say the first part of the fractional part is going to be, instead of 1 upon 10, it's going to be the value of 1 upon 2, and then the next one will be 1 upon 4, and then 1 upon 8, and 1 upon 16, 1 upon 32, and so on and so forth. So it means that this number 625, well, the number 625 can be represented by 1 upon 2, so that's 0.5, plus the value 1 upon 8, which is 0.125. So that means that the binary part of this is going, the fractional part of this, is going to be 1 times a half plus 1 times 1 upon 8. And the value of 1 upon 4 doesn't exist here, we don't need it, so we're simply going to have this value here, 101, to represent the fractional part. Now the problem with representing numbers using this fixed point format is that it's not very efficient. So in this example here we have 132.625, and it's taking as 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11 bits. So as this number here increases, the number of bits here that we need to use in order to represent the number is going to increase as well, and it's just not a very efficient way of doing it. We're not going to get into any more details here in fixed point, we just wanted to talk over this little section here so you understood the number, this number here represented in this binary format. So let's go on and we'll start looking at our floating point numbers. So let's start off by looking at a little bit of theory. Now, as I said before, don't worry too much if you don't understand this little section. it's much easier to understand floating point numbers whenever we go and work through examples. But we need to be able to set the scene here, so we'll talk through a little bit of the theory. Now, I think most of us have seen numbers written in scientific notation. So for example, if you had the number 573 and there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 zeros here, then we can represent this as 5.73 times 10 to the 12. So in effect we take the decimal point up 12 places. So that's 10 places to there, and that's 11 and that's 12, so it becomes 5.73 times 10 to the power of 12. Now we call that there normalised, a normalised form. Now it's normalised because with the position of the decimal point, there's only one figure after the decimal point here. So if it wasn't normalised, we might have, for instance, written it as 57.3 times 10 to the 11. So whenever we're working through our floating point systems, we will be using this normalised version here. So the floating point representation is a similar idea of using this scientific notation. So we're going to use the scientific notation, but instead of using the base 10, we're going to use the base 2. Now for this example here, we're going to use a 32-bit floating point number. Now we could have used 16-bit, or we could use 64 or 128, but the 32-bit is the most common, so we'll start off with our description here using 32 bits. So these 32 bits are split into 3 different sections. There's 1 bit for a sign, there's 1 bit for an exponent. Now an exponent here is, for example, the number 12 or the number 11, so this is an exponent. And the other 23 bits are the Mantissa. Now the Mantissa is nothing other than the number here that we're going to be multiplying. So we're going to have a sign, so it'll be a plus or minus number. It'll have a Mantissa, which is this number, and it's going to have an exponent, which is going to be the power here. So here's a little equation, and we'll explain this in the next slide. So in order to represent this number in terms of a 32-bit binary floating point number, we're going to use minus 1 to the power of the value of the sign times 1 plus the Mantissa times 2 to the power of the exponent minus 127. Now if you haven't seen floating point numbers, that will mean absolutely nothing to you, and this is the point I'm talking about whenever you sometimes learn mathematics and you get this sort of thing thrown at you. So let's go ahead and we'll look at this on the next page, and it will become a lot more obvious what this means. So we've copied over this number here, which is the 5.73 times 10 to the 12, and we've also got our 32-bit binary floating point number. The first bit's a sign, 8 bits for exponent, 23 bits for Mantissa. Now we're going to look at each of these bits individually, so the sign, the exponent and the Mantissa. So the sign bit is very simple. If the sign bit is a 0, then the number is positive. If the sign bit is a 1, then the number is negative. So this makes it very easy for us. So once we've worked out how to do floating point numbers in all of the positive numbers, in order to get it in all of the negative numbers, all we have to do is change this sign bit. So we can see then from the equation we had was minus 1 to the power of the sign. So you'll see it sometimes written like this, and what that really is saying to us is that whenever the sign is positive, the value here is 0. So anything to the power of 0 is just a value of 1. So minus 1 to the power of 0 is 1. So it's going to be 1 times whatever we have left over, so that will just give us a positive number, so it's just plus 1. So this thing here really just says plus 1 in that instance when this value here is 0. Now if we make the sign negative, then it'll have a value of 1. So anything raised to the power of 1 is just itself. So in this case here, minus 1 raised to the power of 1 is just minus 1. So that means it's going to be minus 1 times whatever we have here. So this is going to give us our minus values. So don't worry too much about that. It's just a little mathematical trick that they use in order to represent the floating points mathematically. But the only thing you need to remember here is 0 is a positive and 1 is a negative. So now let's look at the exponent. Now the exponent has got 8 bits. So if you have 8 bits, you're going to be able to represent numbers between the values of 0 to 255. So this means if we have 8 bits, then the exponent can be a number between 0 and 255. But what if we wanted to represent fractional numbers? So for example, if I was to write the number 0.1 and we wanted to represent it, well, 0.1 is the same as saying the value 10 to the power of minus 1. So that would be 10 to the minus 1, and that is equal to 0.1. So that means in order to represent fractional values, we have to have the exponent with a negative value as well as a positive value. So we do that by using something called a zero offset, or it's sometimes called an exponent bias. So instead of being able to represent exponents from 0 to 255, we can actually represent exponents from the values minus 126 to plus 127. Now you might be looking at that and thinking, well, minus 126 plus 127 is actually 253. So you'd be saying there's 253 values here, but up here we've got 255 values. So where have the other two values gone? Well, one of the values is a value of 0, so that takes it to 254. The other value, we retain it and we keep it for some other special purposes, which we'll get into in the next video. But you don't need to bother too much about that at the moment. It's just one little complication that we'll cover at the end. So all we need to know here now is that we've got the exponent running from negative 126 to plus 127, and that's going to allow us to represent fractional values as well as the whole number values. So that means that the exponent value here, which is similar to the exponent value up here in the decimal term, is going to be 2 to the power of the exponent, but in order to get the actual value we take away 127. So this taking away 127 is the offset, and we've created that in order to allow us to generate negative and positive exponents. So let's look at the Mantissa. Now we're going to look at two different values here. There's going to be a normal value and something called a subnormal value, but we'll go into the subnormal value later. Let's just look at the normal value first, and these terms will become apparent whenever we start working through examples. Now the Mantissa is going to be represented by the binary equivalent of the decimal terms here, in the same way that we did whenever we looked at the previous page, and we represented the fixed point numbers here, so this lot here, in terms of the fractional part of the binary representation. So we're going to do the same thing here with the floating point decimal part. So we're going to have the floating point decimal part the same as we did with the previous fixed point value, but there's one other thing that we're going to do here. We're going to actually add the value of 1 onto it. Now we're going to add the value of 1 on because the 1 is actually already understood. There can only ever be a value of 0 or a value of 1. Now if we're using the normal form, then the normal form is going to have a value of 1. So we already know it's already defined as being like that. So we add the value of 1 on here to the Mantissa. So that's an explanation of sorts. It's a mathematical explanation of the little function that we've seen in the previous slide, which determines our floating point number. But let's go ahead and we'll actually look at it in an example, and all of this stuff that we've done here and talked for the last 10 or 12 minutes, it'll all become really quite straightforward. So that's the theory and the mathematics behind us here now. Let's go ahead and we'll just go and work through a few examples. So let's say we want to convert this floating point binary number into its decimal form. So we're going from floating point binary to decimal. Well, the first part here is the sign, so we know the 0 is a positive, so that's going to be a positive number. So that's us 1/3 of the way through. We know what the sign is. So now let's look at finding the value for the exponent. So the exponent is going to be these values here, so it's going to be the next 8 bits, so from 2 to 9. So all we need to do is take this value here and turn it into its decimal equivalent. So we know that's going to be a value of 1, and that's going to be a value of 2, 4, 8, 16, 32, 64 and 128. So that's going to be 128 plus 2, which is 130, plus a value of 1, which is 131. So this is going to be 131. But that's not the whole thing. We have to then take away the value 127. So we take away 127 and we get the value for the exponent is 131 minus 127, which is 4. So that means that our exponent value is going to be plus 2 to the power of 4. So that's us worked out the sign, and we've worked out the exponent. So that's us 2/3 of the way through. So you can see how simple this is. So now what we have to do is work out the Mantissa. Now the Mantissa is the next 23 bits. And all we need to do is work out the fixed point values for these. So that's going to be a value of 1 upon 2, 1 upon 4, 1 upon 8, and that's going to be 1 upon 16, so it's going to be 1 upon 16, plus the next one along is 1 upon 32, and the next one along is 0, so that's 1 upon 64, and then we've got 1 at 1 upon 128, so it's 1 upon 128. So again, that we haven't finished here because the actual Mantissa is that value plus a value of 1, so it's plus 1. So we'll put a bracket around that. Now we'll just go ahead and work this out. You could just put it into a calculator and you get an answer, but let's just work through the arithmetic. So we're going to have the denominator, which will be 128, and we'll have the numerator here, which is going to be, well, 16, that's 32, so it's going to be a value of 8, so 16 goes into 128 8 times, so the 32 will win 4 times, and you'll have the 1 for the 128, and you're going to have 128 upon 128 is a value of 1, so you have your 128 here. So that's going to equal, so that's 128, that's 36, 40, that's 141, so it's 141 upon 128. So that's us actually finished now. We have the sign, which is positive, we have the exponent, which is a value of 4, and we have the Mantissa, which is 141 upon 128. So let's actually just write that out here. So it's going to be a value of 141 upon 128 times 2 to the power of 4. So all we need to do is stick that into a calculator and you're going to get the result, a value of 17.625. So that's us finished that there, and that's us done our very first floating point binary to decimal conversion. So this 32-bit floating point binary number is equivalent to this decimal number here, 17.625. So let's go and we'll work our way back from the 17.625 and we'll get back to the floating point binary number. So this next step is going to be from decimal to the floating point binary number. I've moved the equation out of the way and also shifted this up a little bit just to give us some more room here. So what we want to do is change this 17.625 decimal back into a 32-bit floating point binary number. Now we do that by first of all taking the 17.625 and converting it to a fixed point format, and this is the reason why we went over the fixed point stuff at the beginning of the video. So the value of 17 in binary, well, it's easy enough to work that out, but what we'll actually do is we'll actually do the workings for it here. So we'll have the 17 divided by the value 2. So when we divide 17 by 2 we get 8, and there's going to be a value of 1 left over, so we take the remainder and we put the remainder here, so that's our remainder 1. We then divide that by 2 again, and that's going to give us a value of 4, and there isn't any remainder, so we put 0 for the remainder. We take the 4 and we divide that by the 2 again, and again gives a value of 2 and there's no remainder. We divide the 2 by 2 and it gives a value of 1 and there's no remainder. And then when we divide the 1 by the 2, well, 2 doesn't get into 1, so that's a value of 0 and it's going to be a remainder of 1. So what we do is we read the number from the bottom to the top. So this number here for the 17 is going to be 1, 0, 0, 0, 1. Now in this particular instance here it's not obvious to read it from the bottom to the top because it's the same way both ways in this particular number. But either way, I wouldn't normally work out the value here for a binary value for a decimal number like this. I wouldn't get into that detail. You can just sit and work it out for yourself. You're going to have the value of 1 for a value of 1, 2, 4, 8 and 16. So it's 16 plus 1 is 17. So it's quite straightforward to work it out. But if you want to, you could do it like that. Now for the fractional part, we do the opposite. We don't divide, we multiply. So we're going to have the 0.625 and we multiply by the value of 2. So 2 times 0.625 is 1.25. So if there is a whole part here, then we take a value of 1. Okay, so that's a value of 1, and it's going to leave over the 0.25 part. Okay, so it's going to be 0.25. So just to be clear again, we've multiplied that by 2 and it's given us 1.25, but we take the 1 over here and we're just left with a 0.25. So we multiply this by 2 and it's going to give us a value of 0.5. So there is no whole part here, so we just put the value of 0 and we do the multiplication again. So we're multiplying the 0.5 by 2 and it gives us a value of 1. So we put the 1 here and that's us finished when we get to a value of 1. So if we didn't get to the value of 1, we would just continue doing this, and it could in effect go on forever and you could have a repeating value, but we'll see that in some other examples. So in this instance here, we're going to read this from the top down. But again, it's the same both ways in this particular example, so you won't actually see the difference here whenever you're looking at this particular example. But the value here then for our fixed point number is going to be 10001.101. So that's us almost finished this. In order to get the exponent, what we have to do is we have to move the decimal point here up to just before the very first one. So in this instance here, we're going to move the decimal point 1, 2, 3, 4 places. So the decimal point is going to move to that point here. So that's why we call it floating point, because the decimal point can float up and down. So we've moved the decimal point 4 places. So that means that the exponent is actually going to equal a value of 4. But as we've seen previously, we subtracted off the 127 when we went from the binary to the decimal. When we go from the decimal to the binary, we have to add on the value of 127. So that means that the exponent here is now going to be a value of 131. And you can see that there is the same 131 we had up here. So we can write our sign bit as the 0, and we can write our exponent as 131. So 131 in binary is the number we actually have up here, and that's what we started with. So it's going to be 1, and there's going to be 1, 2, 3, 4, 5 zeros, 4, 5 zeros, and a 1, 1. So that's us got back to the sign part here, and we've got our exponent part here. So let's look and see how we work out the mantissa. So we moved the binary point from here 4 places, 1, 2, 3, 4 to this point here. So what we do is we take all of the values to the right of this point, and these values become our mantissa. So the mantissa now is going to be the value of 0, 0, 0, 1, 1, 0, 1. And as we said before, that in the previous one we did here, that we added the value of 1 on in order to get the mantissa. So in this instance here, we're actually subtracting the value of 1, so we're getting rid of this 1 here. So that 1 in fact disappears, and this is the mantissa that you're left with. So this is our mantissa. So now we'll write this mantissa down next. So we're going to have 0, 0, 0, 1, 1, 0, 1. Now this isn't a full 32-bit number, but what we're going to do is we're just going to pad it with zeros. So we've got 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So we're going to have to pad that out, so it will be 17, 18, 19, 20, 21, 22, 23, 24, 25, 26, 27, 28, 29, 30, 31, 32. So this here is our floating point number, and that should be the same as the number above. So just have a little check. We've got the 0, we've got the 1, and then we've got 5 zeros, 1, 1. We've got our 000, 1, 1, and a 0, 1, and then all zeros. So that's us now looked at a full conversion from the floating point binary to the decimal, and then from the decimal back to the floating point binary. In the next video we'll go over 4 or 5 examples of conversion from a 32-bit floating point binary number to the decimal number, and back again from the decimal number to the 32-bit floating point binary. Once you went over 4 or 5 examples, this will become pretty straightforward. Now we're still to go over the subnormal values, and we'll go over that in a different video. And we'll also cover looking at the ideas of the numbers like infinity. So thank you for listening. I'll get you in the next video. Goodbye.